Welcome to Ask and Learn.
So in this problem, we have a block of mass 2 kilogram is at this point, the block is of mass 2 kilogram moving with a velocity of v naught, which is given by it is 1.3 meter per second. It just strikes a spring which is kept here with a force constant of 120 newtons per meter. And this surface has got the kinetic friction coefficient of 0.3, it says. And it strikes a massless spring with a velocity of 1.3 meters per second. So what's going to happen is that now this block is going to compress the spring. So the spring is going to get compressed and it's going to come to this location. So at this location, we have x naught, which is equals to 0. And at this location, we have xf. So the block actually travels a distance of xf towards the right and comes to a stop. And v naught is equals to 1.3, and then when the block comes to rest, vf is equals to 0. Now we'll write the equation of conservation of energy for this non-conservative force situation, which says that the change of kinetic energy plus the change of elastic potential energy is equals to the work done by non-conservative force. The work done by non-conservative force is actually the friction force, which is minus force of friction times L, the distance traveled on the ground. So if you rearrange this equation, there is one more thing, is that this negative sign is because the force of friction is opposite to the displacement. So the block is moving in this direction and the force of friction is acting in this direction, trying to stop it. So therefore the work done is negative. So if we'll write the equation, we'll get delta K plus delta U plus force of friction times L, that equals to 0. And we'll use this equation here. So now I'll write the equation half m vf squared minus v naught squared, which is delta k. Delta u is equals to half k xf squared minus x naught squared. We know x naught is 0 and we know that vf is 0. Plus force of friction is mg mu k xf minus x naught. So the term which will cancel, the x naught, and then we have x naught, and then we have half mvf squared minus v naught squared and vf squared. So we'll write the equation finally as half kxf squared, because x naught squared is 0, so that equation, that term will vanish, plus mg mu kxf, x naught will vanish, and minus half mv naught squared, because vf is going to vanish, and that equals 0. As you can see that this equation is a quadratic equation of ax squared plus bx plus c. So we have this ax squared plus bx plus this constant half mv naught squared plus c. So we'll solve this quadratic equation by the formula x is equals to minus b plus minus b squared minus 4ac over 2a. So therefore xf is equals to minus mg mu k plus minus square root of mg mu k squared minus 4 times half k minus half mv naught squared divided by 2a. So if you solve that, you will get minus mg mu k plus minus mg mu k squared plus k m v naught squared divided by k. So simplifying that, we will get mg mu k over k, I'll just take it outside, minus 1 plus minus square root of 1 plus k mv naught squared over mg mu k squared. Now we can plug in the values in this case, and you will see that you will get the answer of 0.1258 or 0.13 meters. Now for the B part, the block is kept here and it is in the compressed state. So to remain at the compressed position in this case, the minimum coefficient of static friction, mu s, the magnitude of the force exerted by the spring, okay, which should be equals to the coefficient of static friction times mg, or the static frictional force. So we don't want the block to move. So when the block is actually compressed to the maximum position and it comes to a stop, the force of static friction is just sufficient to keep the block at rest. So for this condition, we have kxf should be equals to mu s mg. So if you solve that, mu s should be equals to 0.77. Now for the third part of the problem, it says if the static friction is not large enough to hold the block in place, then the spring will push the block backwards towards equilibrium position. So we have the block kept here and the block is compressed. In the B part, the static friction force was just enough to balance out the force of the spring. But let's say if it is not, then the block will go towards equilibrium position and then the block will detach from the equilibrium position from the decompressing spring. So for this condition, we again will write that V naught is equals to 0 and XF is equals to 0. And we'll write an equation of the conservation of energy delta K plus delta U plus force of friction times L should be equals to 0. So we have half m Vf squared minus V naught squared plus half K xf squared minus x naught squared plus mg mu k xf minus x naught squared is equals to 0. So for this scenario, we'll have half m Vf squared, because V naught squared is going to be 0. At this case, the block is initially at rest. So therefore, V naught squared is equals to 0. So we need to find out this final velocity for this condition. Minus half k x naught squared, because xf is equals to 0 at the equilibrium position here, plus mg mu k x naught, that should be equals to 0. So if you solve that, then we should get Vf is equals to square root of k by m x naught squared minus 2g mu k x naught. So we can just rearrange this equation, and plugging in the values of this equation of K as 120 Newton per meter, and this is mass as 2 kilograms, and X naught is 0.1258, G is 9.8, and mu K is 0.3, and X naught is 0.1258, we get 0.458 meters per second, which is approximately 0.5 meters per second. So that is our solution to the C.